Okay, good afternoon again. Shall we start? I think most of you are here, I guess. Okay, some of you have replied by email the methane molecule, right? Tetrahedral structure. I think 6-7 people have, or 4-5 people have sent it back. Yeah, you will get. There are how many? Nine vibrational modes are there in methane. What about how many IR and how many Raman? Can you just check your notes and tell me? Tetrahedral methane. Nine vibrational leads of freedom. So 9 modes will be there. So yeah, answer how many will get it? I mean, what are the translation of vibrational modes?
So A1 plus E plus 2T2, the total vibrational modes. A1, E, and 2 times T2, it was total vibration mode, 9 modes.
T2, right? Okay. So this is total vibrational. How do you get how many IR peaks you will
So
get? How many Raman will
T2 is IR active, and all these three are Raman active.
all these things are Raman active. Okay. So who answered this?
So Robin,
Robin. Okay. So I leave Robin. What about others? I think Robin is reading again. I think right. Robin studied a group theory earlier, right?
yes, sir, I have studied it earlier.
Okay. So Ritik,
Yes, sir.
Pansar. Yeah. You
Yes,
tell me
sir.
how many Raman will be there? Raman peaks.
Sir, A1,
Uh,
uh, sir, IR active modes will be 3
what are they?
and Raman active modes will be 6.
How you got that?
And that will be A1, E, and T2.
No, your answer is wrong. How you get this answer? 3 IR. How?
3 IR, sir. Total 9.
Total 9 vibration.
Total 9 modes and Raman active will be A1, E, and T2.
All 3. Huh?
Yes, sir.
Okay.
And IR will be T2.
IR will be T2. Okay. So how do you account for 9 then?
Sir, I'm telling total vibration modes will be 9.
Yeah, total is 9. Agreed. In this 99 are there. But vibrational modes sum up is that should be when you add it up IR and Raman, that should be 9, right? Or individually it can be 9.
Yes, sir.
So Raman, let me. I don't know. I mean, I'll just tell you. So I think you have the character table, right? I think if you have the character table, I don't want to write the in between one. I just mention only the other 2 columns. So A2 is also blank. E has think here you will have E. So this is for E. T1 is rotational, whereas this one will be blank. And then T2 will be XYZ. And this one is XY, YZ, ZX. Okay, so total vibrational is 9. So I think how we do is you write the reducible form of the matrix, and then reducible representation you write, and reducible representation for this molecule is I don't write everything, so it will be 15, 0, -1, -1, 3. Okay, gamma reducible. From that you get the total. Total is total degrees of freedom will be, so you can say 3n. That is A1 plus gamma E plus gamma T1 plus gamma T2 2 times or 3 times. So total will be like this, and then translational vibrational is subtracted. So translational is T2. There is one T2, and then vibrational is T1 is translational, and vibrational is T2. So you subtract that, T1 gets cancelled, and then one of the two will go. So that's what we have written. Gamma is vibration mode is this one. So how do you account for 9 vibration modes? So this is 1 dimension. So this is 1, you can say, and this is 2 dimension. This is 2. Or degenerate, doubly degenerate. Okay, E is doubly degenerate. So you can get 2, and here it is 3. 3 into 2. So you get 6 here. Here 2 plus 1. So total will be 9. Okay, so that's in that way you are getting 9 vibrational modes. In that, how do we know it's IR out of 9? So what are IR modes? You can write which one is that. So IR mode, that should be partition. I mean this one, right? XYZ you have to see. So T2 is IR mode. So there are 2 T2s. So it will give 6 peaks, or I mean it will give only 2 peaks, and each will be triply degenerate. Okay, not 6 peaks, 6 modes. 6. It accounts for 6 vibration modes. It's triply degenerate. Okay, so that's what I mean. Yeah. So T means it's a triply degenerate, and there are 2 times, so there will be 6 vibration modes you have counted. So IR peak, you're supposed to get 6, since they are triply degenerate, you will get only 2 peaks. Just two peaks you get. And similarly, one can get for Raman. So I was telling this column is for the Raman modes. We'll just shortly see why it is taking this one for Raman. So gamma R. So if you see here, vibration modes A1 is there. So A1 is this one will have. So A1 will be active in Raman. And then if you see E is also there, vibration mode. So this is present. So E will be there. And then the last one is T2. So T2 again, the last column, you can see X, Y, Y, Z, ZX is there. Again, so all 3 will be active. So all 9 peaks. You should get all 9 vibration modes active in Raman. So you should get 4 peaks. Here 1 peak for A1, another peak for E, another 2 peaks for T2. At 2 different energy level it will give. So there will be all 9 vibration modes are Raman active. Okay, so there is 6 vibration modes IR active, and all 9 vibration modes are Raman active. Okay, you agree? Ritik?
Yes, sir. Yes, sir.
Yeah, okay. So somebody else has sent an email with attachment. There was some wrong in that. So just please, others, please cross-check it. Okay. So like this, we have to analyze it. Like you first get the reducible representation, then IRs. That subtract with the translation vibration, you get vibrational modes, transfer rotational, and then you get only vibrational modes. And then you see the dimension of the IRs. So this is double DE means the two peaks combined to give only one signal, and then T means the three modes combined to give only one signal. So that is to be represented. So number of peaks will reduce. So methane you will have something like both IR and Raman active, and then you get this. Okay. With this background here, and there was another question one of you have asked by email. How it is totally symmetric will give IR peak. Yesterday I was talking about the direct product, right? Yesterday. I just again touch upon that before you go to the Raman. So whenever, see, every molecule has different electronic states, agreed? This is a ground state, electronic state. That could be a vibration excited. I mean, there could be excited states also. So we're not considering that. So in a given molecule, say this is R, this is energy. So you have various vibration levels, right? Until the continuum just continues. Here also you will have various things. So when a light of frequency falling in IR range falls on this molecule, and say molecule is present in the ground state, okay, so d equal to 0, d equal to 1, like that, 2, 3. So if the light falls on the molecule, okay, so H nu. So what happens? Molecule gets excited, right? The molecule vibration, it undergoes vibrational excitation from one state to another state. Only when the energy matches. Okay, that's what we have studied. So here, not only the energy has to match, energy gap has to match, but also the symmetry has to match. That's what we're looking at. So this is one of the. This is vibrational state V equal to 0. This is vibrational state V equal to 1. So this is what we wrote. Chi initial gamma of x whatever we wrote yesterday, right? And then chi of j. So this can be considered as chi of initial or mu equal to 0 state, and then x, and chi of nu equal to 1 state. So molecule present in V equal to 0 state, that symmetry you have to write here. That is A1 symmetry or B2 symmetry for water molecule consider. So this is A1 symmetry, which is the ground vibrational state of the water molecule. And then excited state, vibration excited state is nu equal to 1, and then that symmetry say we are considering B2. And then the molecule has to, the excitation should happen in certain orientation. It could be X, Y, Z. You know? So only it happens in certain direction, it will give highly symmetric geometry or highly symmetric, totally symmetric representation. Then it will give you a peak. So yesterday I was talking about A1, B2. If you take A1, B2, then mu y will be non-zero. So if you take mu x will give what? So this is B symmetry, right? B1 symmetry. So this will result in this will be this will not give A1. This will not be equal to A1. So mu x will be 0. The dipole moment change will be equal to 0, and it will not result in A1. Whereas if you take A1 with say gamma y, which is again B2, so this is A1 multiplied by gamma y is what symmetry? B2 symmetry. If you see the value table of C2V, you will find. So y, the dipole moment component is in y-axis. Then you take that symmetry B2, again B2. So this will result in BA, 2 into 2, 1, again A1. So this will give, so I'm just putting the direct product. So this will result in A1. No? Here mu y will be non-zero. So molecule has to excite from one vibration state another excited state, should have the symmetry of A1 and B2, the two states, and the dipole moment component also should be say Y component. Then the transition is allowed. Okay, then you will see a peak in IR spectrum. If it is symmetries are matching, say A1, B2 is there, the molecule vibrates in X direction. The water molecule vibrates in X direction. Then its symmetry, the dipole moment component is B1 symmetry. So that integral, we are talking about the integral, right? The integral, when you do that, it will not result in A1 symmetry. So those are not allowed. I mean, it won't give peak. Although there is excitation, but it won't give a peak. So that is not allowed. That's what in spectroscopy we say like that. Okay, so I think similarly you can take A1 into A1 also, and then its corresponding component you have to see. So basically the two extreme things we are taking, right? These are initial and the final state, final symmetry of the corresponding vibration states. Okay, so in dipole moment, this is the should components we take. Now polarizability also the same logic, because now let's come to the Raman spectroscopy. So whenever the radiation falls on the molecule, the radiation has an electric vector, right? So there is an electric vector of E that may induce a dipole moment in the molecule. So when it induces, so dipole moment in the molecule, there will be change in polarizability of the molecule, because dipole moment is given as alpha times of E vector. The electric field of the radiation results in the inducing the dipole moment in the molecule, and that corresponds to the polarizability. So there should be a change in polarizability of the molecule. So whenever there is a change in polarizability of the molecule, so the polarizability corresponds to the binary products. Like if you see in the calculator table, all the binary products, x, y, y, z, z, x, or z squared, or x squared minus y squared. There are other terms we call also x squared plus y squared. So there will be 9 terms in polarizability binary products. So one has to see. I mean, again, the concept is similar. So here, like in IR spectrum, Raman also you have to consider the I mean, it has to result in a totally symmetric representation. So, so here again you can write change in dipole or polarizability. So you can say this guy of I gamma. You say you have x squared. So this is for IR, and this is for Raman. You can say so. This is v square by j, or any other. So this should be equal to A1 or totally symmetric representation, So in water it's A1, but there should be a point group having AG point group or A prime point group. So it should be the first point group in the first IR in the calculator. That is called as totally symmetric representation. It should be chi I, say xy chi z. So if you evaluate that, so it should be equal to totally symmetric representation. That means it's there will be a change in there will be a induced dipole moment, which results in the change in polarizability of the molecule. So that will give a Raman spectrum. Okay, so the concept is similar. What we have seen for IR in Raman also, instead of x, y, z, you have to consider the binary products x, y, comma, y, z, comma, z, x. comma x square minus y square, and other one x square plus y square plus z square. So there are the various binary products possible. So those peaks will be Raman active. Okay. Let's see the bonding properties from a character table. Okay, now let's go to the next one. This is for Raman. You can say Raman selection rules. Here also both the vibration, the molecule has to vibrate from one state to another state in this binary combination, z square or xy yz, and then it should result in a totally symmetric representation. Then it will result in Raman peak. Otherwise, it won't give you any signal. Okay, that's what we're saying. So let's go to the bonding. We'll just see one example how we can say molecules are, which orbitals are involved. To know, I mean, the pi bonding, which pi bondings are involved in coordinating other atoms. Let's take BCl3 molecule. Okay, so BCl3 is B here. You can say Cl, 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 right? So it is a D3H point group. So BCl3 D3H. In this case, there are two orbitals. You can say we just take the. Our aim is to find out the these bonds are made up of which orbitals. Okay, so from character table or from group theory, you can find out. Let me see. Like, so say this is. There are we just consider 3 point charges. In that, we just take the vectors. So pi orbitals. We are going to see the pi orbitals. So let's consider this as A1, and then A2 is this. Say A2 is this. Let me draw, then we just see. So this is A3. So you have a BCl3 molecule. It's on the plane, and then 3 pi orbitals are present on each chlorine atom. Okay, so there are 3. So we are considering only 3 chlorine atoms, which are above the plane. You can say the BCl3 is on this layer, and then all 3 pi orbitals are present. So you can just consider it's plus pi lobe of this molecule, and we take another lobe px or py. So that is perpendicular to this. So this is, I call it as A4, the orbitals. And this is say this is A5, and I call this as let's say this is A6. Okay, right. So this is clockwise, right? So this has to be A6. So basically, what we are doing is we are taking the pi orbitals, which are some are in plane and some are out of plane. You can say out of plane. Okay, so in plane means it is along with the bonds. Okay, whereas out of plane means it is just coming out of coming away from this. So basically, we are considering 2 vectors. So basically, you can say something like this. We are just considering. Okay, so this is plus and this is plus. So we are taking something like this. One is out of plane, other is in plane. So let's write. I call this as gamma of. Okay, so I represent as IP. We call this as OP. Okay, so let's write the reducible representation for D3H. So if I write it here, it's too big. So you can refer the D3H point group character table. So our aim is to find out which bonds are made up of. I mean, these bonds we are writing by line, right? So you want to say which orbitals are involved in bonding. Okay, which are filled orbitals, which are not. So that can be found out and its symmetry. So let's write D3H scatter table. This is 2 times of C3 and then 3 times of C2 and then this is sigma H and 2 times of S3 and sigma V will be there. Sigma V 3 will be there. Okay. So writing is too much, and then let's write only for gamma of in plane. You can say out of plane also. OP we write. So I call it as OP. So can you write it for this? What is the reducible representation for out of plane pi orbitals of BCl3 molecules? Out of plane are A1, A2 and A3. Okay, so this is A2 and this is A3. So you have A1 which is going out of the plane, A2 is again out of plane, A3 out of plane. So if you perform this, only 3 we are taking 3 vectors. So this is E is 3 and then C3 if you consider, if you rotate the molecule, say you are rotating it, all the atoms are interchanged or losing its position. The orbitals have changed its position, so this will become 0. Since C3 is 0, S3 also will be 0. Okay, now let's rotate along the axis. So if you rotate along this plane, C2, right? C2 is just flipping it. Just if you rotate it 180 degrees, 2 atoms will be changing its position, so it gets cancelled. Whereas if you are monitoring A1 by rotation, it becomes -1. So you have a molecule, and then the pi orbital, say pi z is coming out of the plane, yeah, and then you are rotating it 180 degrees. So if you rotate it, so pi z will become -py, or this one will go inverse. That's why it is -1. You can take either A1 or A2, or A3. Either one you can take. Other 2 atoms will be changing its position, so that gets cancelled. Only one vector will be interchanging it, so that's why it's -1. And then sigma H is cutting the plane, cutting the molecule off. So all the atoms will be in the same place. Its lobe, pi lobe, will be inverted. So if it is like this, after sigma H, so it will become minus plus. So it just gets inverted. So, but all 3 are possible. So it becomes -3. So we are looking at the out of plane molecule, out of plane orbital, and then last one is sigma V. Sigma V is also something similar to C2. So again, you cut the molecule off. This will be interchanging, so that gets cancelled. And then sigma V we have if the orbital is top, and then if you're placing a mirror, nothing is going to change. So this will be +1 only. Okay, this is a reducible representation for out of plane orbitals in BCl3 molecule, considering only the 3 extreme atoms, Cl, Cl, Cl. Boron we are not taking, okay, only we are taking only Cl atoms, and then this is out of plane orbitals. Let's write it for in plane orbitals. In plane is this is A4, A5 and A6, so 3 vectors located in 3 different atoms. So again, E will be +3 only. Again, C3, if you rotate the molecule, C3, all atoms are interchanging. So this place or 0. And now C2 will be interesting. Let's apply C2. So C2, if you apply C2, so what happens? So you just rotate the molecule. These 2 atoms interchange, whereas A4 become what we are doing is we are flipping this, okay, fine. So if you flip it, these 2 atoms get 0, and then in plane will what happens? In plane also becomes negative. This will become A4 will become -A4. So again, this is also -1. Not So S3, I think C3 is 0, S3 is 0 here. Sigma H, if you apply Sigma H, here all the atoms are at the same place. So basically, we are looking at this orbital, plus minus, and then in that we apply Sigma H plane. So if you apply Sigma H, it's not going to change. It will just remain as such in all three atoms. So this will be plus 3. Okay, and then S3 is 0, and last Sigma V will be Sigma V cutting into this. So you are just, these two will interchange, that will become 0. And then only A4 will become, if you apply Sigma V plane, this will become plus minus. So it just inverted. So this becomes minus 1. Okay, can you follow this? How I wrote the reducible representation?
Sir,
Yes.
sir, can you explain the sigma h for out of plane? Sir, how it is -3?
Sigma?
Sigma h for out of plane.
Okay, so Sigma H, let me erase everything. It's confusing. So you have, you agree this orbital present here for say one chlorine atom, and then it goes to another. It goes to, I just draw only the. Okay, I'm just leaving out all the atoms or all the signs. I'm just writing this is A1, this is A2, this is A3. Okay. So say you take the molecule like this, and then you have 3 pi lobes, 1, 2, 3, 3 positions, which are just coming out of the plane. That's out of the plane lobes, right? So if you apply a plane, so you're going to cut these 2 into 2, this into 2, this into 2, right? So it will just cut into half. So all after this, apply sigma H. So this will be inverted. So this will become minus plus. This will become really big. So this will become minus plus. This will become minus plus minus plus. It's very simple. I mean, the pi lobe just inverted. Like you take a benzene molecule, you cut into half. All the pi orbitals will just flip, right? All the plus sign will become negative sign after the sigma H plane. Same thing in BCl3 also you apply. Just cut the molecule, slice the molecule, cutting all 3 atoms, and then its lobes are inverted. So since it is inverted, all 3 atoms are inverted. 1, 2, 3. That's why it's minus 3.
Okay, sir.
Okay. And why it is minus plus 1 here? Because when you place a mirror, say here, sigma H you are just placing, right? These two will be interchanging. A2 and A3 will interchange. So that is 0. Okay, you don't count. So this is you have to just consider the unshifted atom. By placing a mirror, these 2 atoms are shifted. So that gets cancelled out. So unshifted atom is only 1. Yeah. So that's why it is just plus 1 here. Okay. Out of plane. If it is in plane, means it will be somewhere here, plus minus. So if you cut it, the plus will go to minus, minus will come to plus. That's why it is minus 1. Yeah.
Okay, sir.
I
Okay,
hope
sir.
other than Robin, others also should follow. Okay. So Robin, I think he's expert in group theory, it seems. So he already read it BSc. I think others also should follow. If you have others have problem, let me know. Okay. We'll redo it. Because say I'm just giving 1 or 2 examples, but
So why the in plane arrows are not in same direction, like
arrows are
or
not,
same axis?
it doesn't matter. It doesn't matter. You are asking why the arrows are different, right? I just consider it's all symmetric. It's all clockwise rotation. You can take this way also. It doesn't matter. Say I consider based on the pi lobe. So basically, we are just building this as 1. So this is 1, this is 2, this is 3, right? And then there is another pile here, plus, minus, this is plus, minus, so this is plus, minus. So just to say these are all plus, minus are in the same form. So this is plus is right side, minus is left side. So the plus is right side, minus is left side. Again here plus is right side, minus is left side. So for that purpose, I have written the arrow mark other way, but it doesn't matter. It just gets cancelled out. It doesn't matter. So just to, since we are considering our orbitals, so that's why I have written this arrow this side. It doesn't matter. You can consider this also like this. Okay, it doesn't matter. So you can take any direction. I just consider symmetric. That's what I have done it. But we are looking at the pi orbitals. Okay, px and pz. So now we got the, I hope you got this, okay. So we got the reducible representation. Now I have to write this, the D3H point group IRs. So there are series of IRs, right? So if you write, I will not fill the table, you fill it. I just give this, I'm worried about the right, extreme right, okay. So this is A1, P0, so this is in plane. So there are point groups like A1 prime, A2 prime, E prime, A double prime. There is 1. A double prime 2. Again, E2 is also there. Right? No, E double prime is there. So last is E double prime. So you have so many things. 3, how many? 6 IRs are there. I'm not writing everything, so I just write only the relevant portion. So you have A1 is x square plus y square plus z square. So you can just Google it. You will find the character table for D3H. That will be much better. So there's nothing here. There's nothing here. No, it's not nothing. It's RZ. Rotational in Z axis is second one. A2 prime. And then third is E prime. E prime is XY, comma Y. And x square minus y square and xy. This is E prime. A1 double prime is nothing. And then this is Z. This is Cartesian coordinate Z. And then there's nothing here. Then last one is Rx, Ry hoga. RZ ho gaya. So it is XY ho gaya. X Z and ZX. That's it. So you should get like this. No, ZX, YZ. Okay, so I think if you see the character table of this, you will find this. You can fill this. Huh? Okay, I'm not writing these characters of D3H. So these are the important things. So now you will get. This is a reducible representation for out of plane orbital. This is a reducible representation for in plane orbital. Then you got this representation. Now you know how to reduce it. Okay, so you can reduce that and find out the orbitals for in plane and out of plane. The symmetries for in plane and out of plane. So for T2 is what? This is double prime. So it will end up something like this for out of plane A2 double prime and E double prime. And similarly for in plane, you will end up with something like this, A2 prime and E prime. So this is for in plane orbitals. So this is I'm getting after going from this is reducible from separation, right? From here I'm getting IRs, and these are the non-zero things. Okay, others will become zero. A prime, A1 prime, A1 double prime. Those things will get zero. Only these two will survive for out of plane, and these two will survive for in plane. Okay, I think you can do this, right? If not, work it out. Okay, so that's a homework. Just work it out. This is homework. This is the IR. So various IRs I got for out of plane, and then this is for in plane orbitals. And I've already done this reducible representation for out of plane, in plane. So what it means is, if you see this A2 double prime and E double prime, A2 double prime is here. A2 double prime is here, just fourth one, right? So it's 1, 2, 3, 4. So there's nothing here. So A2 double prime. No, this A2 double prime is here. The fifth one has Z orbital. So PZ orbital. This corresponds to PZ orbital. Okay, so out of plane is PZ orbital, and E double prime is last one. So last one is these are D orbitals. So D, XZ, and then D, YZ. So this corresponds to PZ orbitals and DXZ and YZ orbitals, or having the out of plane orbitals, and in plane orbitals if you see IP. So A2 prime. So A2 prime is here. Second one, right? 1, 2. A2 prime. Second one is rotation. So there's nothing. It doesn't correspond to anything. It's only rotational vectors are there. And E prime. If you see the E prime, it's here. Third one. 1, 2, 3. So this is both are there. So this is PX orbital, comma PY orbitals, and D orbitals. D x square minus y square and D xy. So this is for the, so from the Cantor table we are finding out for this orbitals. So the out of plane orbitals has A2 double prime symmetry and E double prime symmetry. That corresponds to PZ orbital and D xy and xz and yz orbitals. Okay, so in but pi orbitals are only P, or we consider BCl3. We consider BCl3, right? So Cl has no d orbital, so it's only S and P only, and boron has only P or S and P orbitals. So we don't have to consider these two d orbitals in our consideration. So only PZ orbital corresponds to out of plane orbitals, and in plane orbitals corresponds Px and Py. So in this molecule, so you have this is in plane orbitals, and you have also out of plane orbital. So boron has a unfilled orbital, so that corresponds to the, you can write. So this basically this bond is made up of Sn and Px Py. Basically, in plane bonding is symmetric S orbital also along with Px and Py, because if you see A2 prime, it is written as x comma y in combination. So in combination means it will go together. X and y go together. It could be either one. So we have to consider this bond is made up of S and Px and Py orbital, whereas the unfilled boron orbital and chlorine orbitals are made up of PZ orbitals. So basically here, so out of plane, this is out of plane orbitals, right, which are just coming out of the molecule. So that is made up of pz orbitals. So these are all pz. So okay. So like this one can report it. So this in-plane bonding is through S and Px Py, whereas out-of-plane orbitals are of Pz type. And if there is a bonding taking place between boron and chlorine, that is also happening through Pg orbital can donate the electron to the empty boron orbital by Pz, only through Pz orbitals. Whereas there is a coordinate bond between boron and chlorine, then those are made up of they are present in S and Px Py orbitals. So this is what we can infer, which orbitals are present in involved in bonding from group theory using the Faraday table.
So can we use another method for finding the orbital of orbitals involved in hybridization?
Can you repeat it when you spoke? No,
As
it
I
was
have done group theory in undergraduate, and we follow some different method to find the orbitals involved in hybridization.
okay. I mean, either way, yeah, you can find, you can
We can do by
either way.
number of shifting bonds.
Yes, yeah. So I was saying no, unshifted atom. Some books follow that method also. That is also okay. Either way, you can use it. Okay.
Okay.
It depends on which book you follow. Based on that, you can explain.
Sir,
Yeah.
I have one more confusion regarding the group multiplication table, and I have sent mail to you regarding that also.
You have sent a mail regarding somebody sent about C3V multiplication table.
Yes, yes, sir.
You have sent it.
Yes, sir.
I will work it out and send it to you. Okay. Yeah.
Yes.
We have the solved solution. I have. That should be fine. I don't know. I mean, I'm not able to. Your image, the photo you have sent, it is really not clear. I will work it out and send you that. Okay. C3V multiplication table.
May I send again the image if it is not clear?
Whenever you speak, there is a voice. It comes
Yeah.
with disturbance.
If the image is not clear, may I send again that one?
Image, kind of, yes, yeah. Or you the one you have written, no, it's all too congested. I'm not able to figure it out what you have done. You have taken a direct product of, you have taken the product of three matrices, right? Sigma V,
Yes, sir.
prime, C3, Sigma V prime.
Actually,
Who is
okay,
Robin?
I will.
You have sent it, I don't know, you triple prime, C3, Sigma V prime. This you have done it, right? Something you have read. I don't know
Yes,
why.
sir.
Then you have written a matrix form and then you are taking a product.
Yes, sir.
Yeah, so
I want to know we have to follow the left to right path or right to left path
right to
for the
left,
matrix.
right to left.
But we
After getting the matrix,
do-
no, you have to do all three together. See, matrix multiplication, you have to do only two only, right? If you have a multiplication table, you have to just take the product of only two only. When you have a
but
matrix,
C3V
you will take it from.
C3V
I'm confused with your question because you have written all three. C3, Sigma V prime. But matrix multiplication is you have to take C3 and Sigma V. If you're taking, this will be a one form 0, 1, 0, 0, 0, 1, 1, 0, 0, and then whatever it is. I am not sure what you have written here, so it could be 0, whatever. I just write it.
Sir, as the C3V is non-abelian group, so when we multiply the matrices of C3 and Sigma V prime, we get different results if we follow the different orders, like C3 into Sigma V is equals to minus of Sigma V into C3. Like this is a non-abelian group now. So which order we have to follow for the multiplication?
So see, if you have three things, you have to go this way. Okay,
If
so
we
right.
follow this way,
Yes.
we get different results from that of group multiplication table.
Table. If you see how you are correlating, let's see. Let me see. Okay. Okay, so I have to check what you're saying. Okay, fine. I'll take it this and then I'll work it out and let it get back to you.
Okay, sir.
Fine. You're saying it gives different answer compared to when you go from left to right. So it is not matching with the multiplication table. That's what you're saying.
Yes, sir.
Yes, sir. I face similar problem.
Okay, fine. I'll take a look. Okay, so this is about the bonding. I'll stop it here. I think today, no, you are 3 o'clock. Your seniors, yeah. Class committee meeting is there. So next class we start using what is called as projection operator to find the symmetries of various pi orbitals. Huckel's MO theory will start. Okay.
Hello, sir.
Yeah.
Sir, I have a problem regarding the quiz date.
Quiz date. See, some your friends have. I mean, all of you have quiz on 16th, right? Friday, I think. So when do you want to write? I think only one person has problem, right? Is
Yes,
it,
sir. Sir, I have exam.
right? Yeah, Bhattacharya.
Yes, sir.
Yes, you are having exam, no, that day.
Yes, sir.
Okay, no problem. I'll give you a separate question paper for you some other day.
Okay, sir. Okay.
Okay, so you happily write your BSc exam, but all others will write quiz, and then once you are done, we'll write quiz separately with a different paper. Okay.
And
Okay.
sir, the syllabus for the quiz is whatever we have done till today.
Yeah. Okay. Take it till today. Whatever you have done.
Okay, sir.
So by today or by tomorrow, I'll send an email how to download it. I think download is simple. It will come to your email ID, question paper. Then upload. You just go to the classroom, Google Classroom, and upload it. I'll send you the details by email. So you have started using the Google Classroom or not?
Yes, sir.
Yeah, so I think you done. It's not a problem. We'll do it. Yeah. So once the exam is over, you have to just convert to PDF file and then upload to the assignment in Classroom, Google Classroom. So there'll be assignment option. So you just upload it. Upload means there'll be a turn in option is there. Yeah. So just do that, and maybe I'll just send an instruction. Maybe those who have not used it may have problem. But now you have to just learn that. So it's automatically comes to me, everybody's reply with the date and time. Okay, so I'll just stop this recording.